Ladies and gentlemen, welcome to Engineering Dynamics. In this video, we will solve this hexapod system. The goal of this exercise is to just work with transformation matrices and how we transform from one coordinate system to another. So our task for this exercise is to find the length of each leg of our hexapod system, given that we have the TCP, the tool center point, and the angles of alpha, beta, and gamma. And those are the current angles. So we first turn around X, then we turn around the new Y axis, and then we turn around the again new Z axis. So the goal is to get the length, or first of all, the vector B1, if we have the given tool center point, and we of course know the position of our leg where it's beginning. And we have this connection from the tool center point to the connection of the leg. So to get the vector that we need, this one, we can also go everything backwards. So we go minus U1 in this case, then we go plus the tool center point and plus O1. The problem is that we have, we have the U, so the position of the start of our leg in coordinate frame I. We have the tool center point in coordinate frame I, but our distance from the tool center point to the connection of the leg is given in coordinate system K. And we need to transform from K to I. Let's remove that. So we have to get from the coordinate frame K to frame I. And we do that with a simple transformation matrix. So we go from K to I. But the problem is that we not only have one transformation, so one rotation around an angle, but we have multiples because we have those cardinal rotation. And they are defined as rotation around X, we have a new one, rotation around Y, we have a new one, and rotation around Z, and we again have a new coordinate system. So we have a new system after each rotation. So here again, we go from I to K, from I to K dash, from K dash to K double dash, to the end system that is our K. And the transformation matrices are written a little bit different because we are going from I to K dash. Here we go from K dash to K double dash. And here we go from K double dash to K. This one is just the angle, the axis around which we're turning, just to have a visual reminder that we're turning around X, Y, and Z. And now we want the overall transformation matrix if we want to go from I to K. So the transformation matrix, or the matrices, are always multiplied from the left side. So that's why we first have this one. We go from I to K dash, then we go from K dash to K double dash, and we go from K double dash to K. And now we can get our vector that we had in the first, that we know. So O, in this case, O1 K in the coordinate system K, and we got it by having the vector in the inertial coordinate frame and transforming it 3 times with the 3 rotations. And if we now want to go back that whole process, we have to again multiply the transformation matrices, but this time we rotate in the opposite angle. So that's what we're doing. The last one that we did, the last multiplication, was the rotation around the Z-axis. So now we, again, from the left side, apply the transformation matrix around Z, then the transformation matrix around Y, and then around X, and each time with the negative rotation. So Here we have the transformation matrix. I rotated it in a mathematically negative way. So because we are rotating around x in this case, x stays the same. This one is our y. So we go y in the inertial coordinate frame. We have a positive sign and a positive cosine right here and a positive sign right there. And for z, we do the same thing. We have z, we have a positive cosine, but a negative sign. So that's right there. And again, rotating in the negative direction. And we do the same thing for beta and gamma. And as soon as we have those two, we can pre-multiply our transformation matrices that we just found right here, right there, and this one. And we get our vector that is shown in a inertial coordinate system, even though we had it in the coordinate system K in the beginning. So if we have this one, we can insert our solution in here and get the vector bi, so for every leg basically. In this case, we're going for b1. So we know b1, and then we just need to get the length of our leg, because that's where we give our physical contraption right here. We just know how much to extend the each leg. We get the length by just doing b1 transposed b and then getting the root of that. So that's how we get the length of a vector, and that's how we know how to tell our simulation or our physical object how much to extend if we know the tool center point and we know the angles that we want. I hope this video gave you a small introduction into transformation matrices and how to work with them. If you have any questions, I will do my best to answer them. Just put them down in the comments. Thank you very much for your attention and see you next time.